Hello, everyone, and welcome to this month's Python Exchange. My name is Cameron Riddell, and I will serve as your host for this evening. Today, we are joined by a very special guest, Dr. Giordon Stark. We also have our usual team of guest panelists here to help us out as well. Dr. Giordon Stark is a death experimental particle physicist with the ATLAS collaboration at UC Santa Cruz. Giordon earned his PhD from the University of Chicago and a BS from Caltech, and now he's on a mission to find signs of new physics beyond the standard model. He's fascinated by everything from boosted objects and jet substructure to the crossroads of particle physics and machine learning. And he's played a key role in combining BSM search results to guide the future of the ATLAS program. When he's not chasing new particles, Giordon can be found in the kitchen, baking sourdoughs, pavlovas, and whatever else catches his fancy. With that said, Giordon, I would love to turn things over to you so that we can go ahead and get started. Thank you so much for joining us.
Sure. And recently I've been doing a lot of lemon-based things, given that my tree is very generous this year. So, we'll get started with the talk on efficient statistical modeling with computational graphs in Python. I should preface this by saying that I am by no means a network expert or a computational graph expert of any kind, but one of the goals of this project when I first started it was to identify the fact that all these different pieces of technologies exist and trying to tie them all together into a coherent interface. So just first slide here is just kind of a brief overview of who I am. You've already heard some introduction from me. Some specific details is that within the ATLAS experiment or around the ATLAS experiment, my time is generally split between working on core input I/O, meaning input-output software for ATLAS experiment, working on the offline software that we have known as Athena. I also work on the Iris Hub consortium on the analysis systems, which is working on columnar analysis, statistical modeling analysis, packaging, reusability, that sort of space. These are things I'm interested in, trying to preserve all the knowledge that we're doing. And I am also one of the cluster systems administrators for the analysis facility that we have at the University of Chicago that has about 800 users or so across the entire world. And it's pretty heavily used, and it's fun to learn more about all the different workflows that everybody's doing. So when we talk about the standard model particle physics, there's usually this typical table that everybody shows, which kind of looks like the periodic table of elements. An alternative picture I have here is to think about all these particles with the different masses, and when you try to change your perspective about what we know of the standard model, you realize that this kind of looks interesting. You see these sort of different generations of masses here. You brings up lots of different questions like why these particles have lots of different masses, what is the nature of dark matter and so on. But we have lots of different questions about the standard model. One of the ways we can answer questions about the standard model is through collider experiments. There are other types of experiments. Neutrino experiments, we also have astrophysical measurements that we can make as well. But for the purposes of today's talk, because that's where a lot of my background is in particle physics, I'm going to focus a little bit more on the collider experiments at CERN. And CERN primarily has the large experiment there known as the Large Hadron Collider, which is a 27-kilometer ring, the yellow 27-kilometer ring that you see there, with 4 primary experiments scattered along one of the 8 interaction points that exist there. The collider ring is a ring where we have proton-proton beams spinning around in opposite direction, one beam that's clockwise and one beam that is counterclockwise. And we cause those beams to overlap using magnet systems at specific interaction points. So we have the 4 largest experiments there: CMS, LHCb, ELISE, and ATLAS. And each of those experiments is situated at one of those 8 interaction points around the ring. And I am part of the ATLAS collaboration since 2014, and that is where I will focus a little bit of the work that I'm talking about today. But a lot of what I'm talking about applies to not broadly all just particle physics in general, but can also apply outside of particle physics across all of physics and across other sciences as well, which I'll briefly mention as part of this talk. The Large Hadron Collider operates in a couple of different runs. We had run 1, which was back around the Higgs discovery 2010 to 2012-ish. That one collected 25 inverse femtobarns of data. Femtobarn is the measure of data that we use to talk about it, and the rough approximation you can use in your head is that about 1 inverse femtobarn is approximately 100 million events, which is 10 to the 14 events. And this is where we do 40 million collisions per second, about a collision every 25 nanoseconds. That's what we call our bunch crossing rate, where we have those proton bunches that are moving in opposite direction crossing at the interaction point. Altogether, this produces about 90 petabytes of data per year. And what you see on the left-hand side is a kind of Wordle sort of equivalent here, where each square corresponds to about 30 inverse femtobarns. Run 1 is the dark green square here. Run 2 collected 150 inverse femtobarns, and Run 3, which we're wrapping up this year, is collecting about 300 inverse femtobarns of data. That's the total amount of data we have. So when we talk about the Large Hadron Collider, we talk about all of these experiments. We're really in this sort of big data regime here, and all of this data we collect serves the goal of trying to answer those questions about this data model. And so the way we do that is through this big picture is on the left-hand side, we have this detector, say the Atlas detector, and that Atlas detector is collecting that data for us, 90 petabytes per year. But then on the right-hand side, we have the sort of brain power contributions from theorists and experimentalists trying to understand how to model everything. Whether we talk about modeling how the detector actually performs, making a digital twin of that detector, understanding the material interactions that happen, and simulate those material interactions, but also in terms of the theoretical model underpinning the Stern model, as well as any future beyond the Stern model theory that we care about, whether that is SUSY or effective field theory and so on. All of these are part of the model here, and we need to have some sort of function that allows us to test any hypothesis we want about our data. Perhaps we come up with some sort of new model, and we need to have that sort of technical ability of testing that theory against the data we've collected so far and data that we've yet to collect over the next 15 to 20 years from the Large Hadron Collider. That's what kind of motivates part of this entire work, and there's already been a lot of work in this space. Nothing about this is fundamentally new, but what is different is to try and take advantage of the current technological advancements that we have today. So a statistical model, if we talk about, for example, the Higgs boson discovery in 2012, we are presented with these sorts of plots like you see here on the right-hand side. There are 3 different curves of interest, which I've zoomed up a little bit on the left-hand side for you. You have these black points of data. This is the data we've collected at the detector, one of the many tens of hundreds of millions and millions of millions of data that we've collected. The solid red line here is a prediction of a model where we contain the signal, in this case, the Higgs mechanism, plus the Stern model without the Higgs mechanism. So you can think of the red line as the current Stern model that we have. Back then in 2012, the current Stern model didn't include the Higgs at all. So the Higgs was seen as some new theory that we were testing again. And the dashed line here is the Stern model that we had at the time without the Higgs mechanism. And for us to test this theory, the fundamental hypothesis that we want to have is the Higgs boson part of the Stern model? So then the question is, you create a model that includes the Higgs mechanism and a model without this mechanism, and these are 2 different theories that give you 2 different predictions, and you say, which of these 2 theories is more compatible with the data? That's the hypothesis testing that we do. It boils down back to high school statistics hypothesis testing, but you really have to build up everything in here. You have to build up the model, you have to build up the data, you have to contribute everything, the systematic, and our understanding of how the detector works and behaves, and any uncertainties that we have about any measurement we do or any sort of reconstruction, whether we understand if this is truly a photon or an electron, or maybe there's some sort of misidentification of whether there's a beam. There's lots of different things that go into it, and all of these models are not very simple. So, how do we make the analysis results that we have out of these experiments interpretable with new theories that come out the next day or next week or a year from now? And how do we combine different analysis results, not only from just the Atlas experiment, but analysis results from the CMS experiment, from the G-2 experiment at Fermilab? How do we combine all of these different analyses that are probing different pieces of the external model to give us a more complete picture? And we need to be able to have what I call serializing hypothesis, which is kind of a terrible hand-wavy way of describing it. But the idea here is that we are building these likelihood functions through statistical models or public probability models, and we need to have a way of serializing all of them. One such proposal is called HS3. HS3 stands for, initially at the time, the HEP Statistics Serialization Standard. It is most likely being renamed now to the Harmonized Statistics Serialization Standard, and it is a proposed standard that has been implemented in a couple of different libraries, primarily Root, for serializing these statistical models and likelihood functions that I was talking about. It's one piece of the bigger picture of trying to reinterpret these results and trying to combine results from many different experiments. On the C++ side, this is implemented in Root. In Python, which is the point of today's talk, is in PyHS3. In Julia will be in hs3.trail. And this was released back in December of 2023. Now, HS3 has been an evolving specification. It is still evolving. It's version 0.2. Version 1.0 will likely be one of the most stable versions we have, but that's not going to happen, not particularly anytime soon, because we need to understand the needs across the field. There is a German-funded project, a BMBF-funded project in the ARM data space under the RDM track that is called DEMOS, Democratizing Models. And this is the space where it will cover nuclear physics, hadron physics, astrophysics, astroparticle physics, and more. And there are, if I remember correctly, 12 or 13 different German institutions covering all of these different physics domains to be able to understand how to take HS3 as it stands today and tie it in with the existing analysis work that's being done there. And I'm also linking the GitHub pages website that you have here. Feel free to take a look at it and understand the bigger scope of how everything fits in together. Right now, Root implements version 0.2 of the specification as of last year, July 9th, 2025. It's not perfect, but it's there. Atlas and CMS experiments have already started publishing some of their analysis statistical models in this format. So, what is HS3? HS3 as a workspace, and this workspace is composed of different pieces here. And we're not going to go into too many details because I like to talk a little bit about PyHS3, but I just wanted to provide some context about the sort of structure in this workspace here. On the bottom, it's kind of JSON level snippet of what that piece of that workspace looks like. You have in yellow, you have on the far left distribution. Distributions are generally the distributions that you're aware of, such as Gaussian or Poisson or Cristobal distributions. These are generally normalized. We also have functions. Functions are just describing more complicated mathematical operations that are, say, a product of different distributions or a product of different parameters that you want to control within the statistical model. You also have in the orange, talking about parameters, you have domains, which are the ranges of those parameters or the bounds in which you allow those parameters to fluctuate within your statistical model. And you also have parameter points, which describe things such as what the initial value of that parameter could be, whether that parameter is held constant when you do statistical inference or not. And this is sort of the high-level overview here. And a model, when we talk about a model, is a specific distribution that you care about. That distribution may reference or use as input other distributions within that workspace or other functions within that workspace, and require a specific parameter point set and a specific domain set, because you can have different ranges or different groups of ranges that you apply to different parameters because you're looking at different base spaces within this entire picture. It's very abstract and very generic and very configurable and flexible for that purpose. But PyGist3 is a Python implementation of the specification. It is able to bidirectionally read in any file that follows that specification, but it can also output any statistical model that you gave it into that specification for being able to be used within root. So you have this sort of cross-language communication through the specification, which you see here on the bottom of my screen in sort of icons here. You can install this using pip, using all your typical Python tools, pip, UC, poetry, what have you. This is also in the Conda ecosystem, so you can use Pixie or Conda or Mamba or, again, what have you. So it's very easy to install, but this is purely Python. It does depend on a couple of core pieces. There are 4 primary core pieces that we have here. Thank you, Cameron, for linking it. The core pieces that we have here are PyTensor. PyTensor is for the tensor computation for building our computational graph. It provides out-of-the-box automatic differentiation and efficient PDF evaluation. It also has the ability of compiling the computational graph in different optimization modes or using different computational operations, including drags, which is very useful. We also have RustWorkX, which, if you are familiar with NetworkX in Python, this is the Rust implementation of that. I just picked it because it's much faster, and I'm personally a fan of Rust, given that I use Pixie a lot in my daily workflow. There's SymPy as well, which is for symbolic mathematics parsing, because as part of this workspace, we have what we call generic distribution and generic functions, where if there is no existing distribution or function that suits your need, you can come up with your own distribution of function and write that as a string, and we use SymPy to symbolically parse that and build up that part of the computational graph for you. And then the final one here is from scikit-hep, which is called Hyst, which is a Python wrapper around the boost histogram implementation for doing histogram creation that makes it easier to visualize these data sets or outputs of these statistical models using, say, matplotlib. This is Python 3.10 plus with modern typing and data class patterns everywhere. So I mentioned very briefly about compilation modes, and I just wanted to mention what I meant here. This is a screenshot that comes from PyTensor's documentation. The bottom that you see here is the ability of generating the model out of the workspace with different compilation modes that you have here. But PyTensor, for example, provides fast compile, fast run, number, drags, and so on. And each of these different modes have different benefits or different gains. You may want to compile your computational graph very quickly, but compiling it very quickly doesn't give you all the different simplification or graph rewrite that will make it very fast or efficient to run. But then you might have, for example, number or drag, which is where it rewrites and compiles the whole graph using number operations or drag operation that PyTensor is aware of. There's a lot of work that goes on in this space, and I'm not going to claim that any of these are better than the other, but I will show you some benchmarking numbers of how some of these modes work out of the box. And there is ongoing work trying to understand how to improve it, how to make this as fast as humanly possible on heterogeneous computational hardware where you have x86 or ARM64 machines. In terms of benchmarking, and this is a very simple, very contrived example that is absolutely not realistic at all, but gives you an idea of what is already plausible. So I'm taking a Gaussian distribution, a very simple Gaussian distribution where I say that the mu value, the central value of this Gaussian distribution is 2, the standard deviation is 3, and I'm using 1,000 points. I'm evaluating that distribution at 1,000 points, and I'm evaluating that 10,000 times. And so then the question is, how fast can I evaluate that Gaussian in all of these different frameworks? Essentially, I'm comparing root against PyHS3 using PyTensor in different compilation modes. I'm also comparing it against a package known as NumberStack, which has actually been one of the fastest ways of calculating distributions. They were number optimized, number JIT compiled in that package. It was up to this point really the fastest way that we had in Python outside of root. Now, if you look at the performance here, root out of the box, if you don't do anything, root is very, very fast. And the reason why it's very fast, and number one, is because it very aggressively caches everything. It caches so much of it that, in fact, when I tried to manually compile root and turn some of that caching off, I only tried to turn off some of it, but I could not turn it off completely. It was still very fast, and that's what you see here, the top two. However, PyHS3 in the fast run mode gave me the third fastest option, and in fact, that was already faster than NumberStack. And you can see here that NumberStack ends up being 6 on this list here, and why PyHS3 is very slow with Jack is another thing that needs to be investigated. But these are very preliminary numbers that already gives you an idea of just sort of the speed up we get. But of course, root is going to be very fast because root is caching everything aggressively, whereas PyHS3 at the moment, the way I've designed it, zero caching done because we're building this up sort of in an academic endeavor where we're trying to understand truly what is the bare minimum we can get away with before we start trying to optimize the library entirely. We need to get that functionality in place first. Kind of don't run before you can walk kind of deal here. So, at this point I haven't shown you any code about PyHS3, so I want to give you a little bit of what that Python code might look like here. And so, as an example workspace, and I believe I have the Hello World example on the next slide. This example workspace that we have here comes from the scikit-help test data, and I provided, let me put that in the chat for everybody. But this is the, to everyone, I need to click that, there. So this is the link to the merge request that adds in this workspace here. So this test data here is a slightly more real-world example. There are 28,000, 29,000 parameters, 540 distributions, and 10,000 functions in this workspace. It's a pretty hefty workspace to start with, and you can see some of the different kinds of distributions that we have here. There's a crystal ball distribution, Gaussian distribution, a product distribution, a mixture distribution. A mixture distribution is a weighted sum, and a generic distribution, which I mentioned before, uses SymPy, where the analyzers are able to write any kind of distribution they want, and it will automatically be built in. And then we also have different kinds of functions here. And at the bottom, you can see an example of what that generic distribution looks like. So this is actually, I would call this relatively easy to work with. You need JSON to read JSON files. You need the scikit-help test data package to load in that test data. And you need PyHS3 and grab the HS3 workspace out of it. And so first we load in that file path from scikit-help test data. We grab that workspace JSON, we just loaded in, and we feed it into the workspace object HS3. And at that point, you can then build a model out of it almost immediately, which is the line here, model equals workspace.model. And there's a progress bar because we're using RustWorkX under the hood to build a dependency graph of everything and calculate and evaluate and build those intermediate compilation graphs of all those individual distributions and inject them into the larger compilation graph. is a very complicated, in-depth process. I'm happy to try to improve this, but so far I am not really disgruntled with how slow it is at the moment. I feel it is fast enough right now, and until I get more users and more people using this, it won't change until I get more feedback. And once we build that model, you can then create all the different parameter values you want to evaluate that model at. You want to call the model.logPDF at those parameter values. You can see here at the bottom portion that I evaluate the model at different parameter values. In this first case, I'm just asking for the log likelihood of this model, this distribution that exists in here. And then what I do is I say fine. Now I want to take the invariant mass, one of the parameters in this model, and change it from whatever the initial value was in this workspace that it gave me, and I want to evaluate it for a different invariant mass, and I'm able to get a different log likelihood value. Those are the fundamental building blocks for doing statistical inference. When we talk about statistical inference and hypothesis testing, the core piece that we need to do, whether you're running it through a minimizer using SciPy or MiniRead, you need to be able to calculate the PDF or log PDF of your model. This is how I describe PyHS3 here. We have, using HS3, the ability to serialize the statistical workspace to JSON. For something like PyHS3, you have the ability of taking that serialized workspace, loading it up, and giving you a call-up function in Python that you can then pass around to anything that needs the likelihood or log likelihood value. That's it. That's the goal of PyHS3. That's where the scope of that project is. And of course, you can see the performance here between where we have fast graph building mode, fast graph evaluation mode, and making sure that there's no computed difference between the likelihood for both modes. And this is about on par with JAX when you do the evaluations for much larger models. In this case, I'm using that same model I showed you on the previous slide, but a slightly less contrived example to give you an idea of what the performance looks like here. I'm still working on trying to give you the same performance numbers with root, but it's just a little bit trickier. But anyway, I hope this kind of serves to show you that we kind of have all these different pieces, all these different tools we're building on the shoulders of Giant, the shoulders of everybody in scientific Python to kind of put this together and give us something that we can work with today to build off and to get us this bigger picture of trying to combine everything. And of course, I mentioned very briefly that I depend on HIST for building histograms, and I was just showing you an example of what I mean here, which is where I could have some sort of bin data within the statistical workspace, and I can just ask for data.toHist and use matplotlib to just plot that. So I don't have to think too much about how to do anything more, and you can kind of almost imagine that now you kind of abstract away the serialization of what you want to plot. And of course, HIST has its own serialization language as well. So there's lots of different entry points to being able to preserve this knowledge in the future, and one way is through the statistical workspaces. So I also wanted, before the end of my talk, which I think I have maybe 2 minutes left, I just wanted to briefly highlight the maintenance or development side of it, because I think it's probably a little bit interesting, perhaps for some of the attendees as well. It's primarily myself and an undergraduate doing all of this work right now. We are expecting, given that the demos, the Democratizing Models project got funded, that there will be some additional contribution from some of our German colleagues as well. I am also using AI tools, primarily Claude Code and CodeFlash AI, to supplement some of the work we're doing here. We have not used AI to generate any functionality, and any functionality we do use, we always cross-check it with existing tools such as SciPy to ensure that we are numerically consistent. And CodeFlash, you might have heard about this very recently, because this was recently used to make Python's packaging 3 times faster. You can read Henry's blog post here about it. I also use CodeVector to catch other issues, And I am very aggressive about making sure that we maintain 100% code coverage. And to date, we currently have every line of code in PyTest 3 fully tested. And I use Pixie for common task and environment management. So if any of you feel like you're interested in contributing to this in some way, you're going to learn how to use Pixie because that's how everything is managed. And I have some acknowledgments here. The undergrad that I mentioned is Alex Smith. I also want to acknowledge some of the people, Lindsay Gray over at Fermilab, who I kicked around this idea, 6 or 7 years ago. But a lot of the tools that I depend on today were not around back then. So I think it just took a little bit of time for all these other pieces that I depend on to come into fruition a little bit. And Karsten Burgard, for his patient also for developing HS3, Lucas Heinrich and Matthew Fikert, who I worked with on PyHub, the factory Python implementation, which was a different statistical related implementation we had, but for a smaller subset of some of the statistical models that we publish in Atlas. And I probably should acknowledge Claude Code a little bit because it's somewhat quite personable. And this is pretty much the end of my talk.
Fantastic. Well, thank you so much. If you're in the audience and you do have a question, feel free to use the chats or the Q&A. I'd also like to take a moment to introduce our host panelists who will help drive some fascinating discussion that I know we are going to have. Why don't we kick things off with James Powell? James, can you take a moment just to introduce yourself to our audience?
Hi, everybody. My name is James Powell. I work together with Cameron, and we work to help bring technical methodologies, programming methodologies to folks who work in fields very similar to Giordon himself. And I would love to hear, as part of our Q&A session, a little bit about the experience in putting together a fully formed open source package for somebody who doesn't come from a computer science background, doesn't come from a computing background, but instead comes from the scientific background.
Amazing. Well, I know we're going to touch on that topic without a doubt. At least I know I am also personally very curious about that. Next up, we're also joined by Thomas Caswell. Tom, would you care to take a moment to introduce yourself?
Thomas Caswell. I'm at Brookhaven National Lab at NSLS2 in the Data Science and Systems Integration program. I'm also the project lead for Matplotlib and a core developer on H5Py.
Perfect. Well, Tom, it's always a pleasure having you, and your expertise and background is very much always appreciated. Last but certainly not least, we are also joined by Doha. Doha is joining us today. And so, Doha, can you also take a moment just to tell us a little bit about yourself, a little bit about your experience with Python and beyond?
Hello, everyone. This is Doha speaking. So my video is open, right?
Yes.
Okay, so I'm a computational scientist at Argonne National Laboratory. I'm at the Advanced Photon Source, which is a synchrotron there at the X-ray Science Division. So we've been doing a lot of computational work for analyzing, for understanding the X-ray data that we collect from various samples. We've been using Python-based tools for controls, analysis for various things, and I'm very interested in basically using and extending and pushing these tools. So thank you.
Fantastic. Well, Doha, it's a pleasure to have you join us. Why don't we go ahead and jump right into a little bit of a discussion? So we'll open up. Do any of our host panelists have any questions or comments for Dr. Giordon Stark? Tom.
So you did answer this a bit because you said root is caching and the other ones are not. And my first thought was, well, can you cache? What sorts of things are being cached by root that you're not currently caching? And is it just a complexity reason, or is it like a technical risk to cache some of those things?
So caching, I would say, is a hard problem, but I don't want to say it's trivial to implement in Python, but there are existing solutions such as using the LRU cache, for example, just sticking that on the top of some function call and just recognizing that it's already been computed, just returning the result. Root is just very aggressive about it because Root builds its own sort of computational graph in lots of different ways. It does a lot of bookkeeping. It keeps track of parameters both at a global level but also at a per model and distribution level. And what makes it a little frustrating is that there are parts of the cache that it maintains outside of the statistics that it's using, meaning the low-level mathematical operations that get called, such as addition or multiplication, it caches at that low level too, which is both clever but also kind of frustrating when you're trying to benchmark things appropriately because it's hard to get sort of an apples to apples comparison. I have been in touch with the Roosters team expert on this, Jonas, because he is also doing his own sort of benchmarking, and he himself has expressed some frustration with the caching because it makes it hard for him to also understand the level, like how performing it is. Root does compile in C++, so it compiles, in my mind, almost exactly the same way that PyTensor should. So my naive expectation is Root and PyTensor should be equivalently fast, but it's hard to really show that or demonstrate that immediately. But I could implement caching on the PyTensor side and try to cheat my way to being faster than Root. I just feel like I don't want to do that.
Doha, yes.
So yes, it was a very nice talk actually. So I learned a lot. So just my question is more like a broadly. So you've been using a lot of Python tools. It's a huge ecosystem, and for this application, so what are the, for example, the bottlenecks, or what areas that you see the Python space should invest more into? Like, is it more in this particular application that you're using? So this is more like a general question. Is it more like a performance bottlenecks, or is it more like accuracy models and things like that, the mathematical modeling things? So what do you think about the whole ecosystem that supports these your basically science application?
So I'm just gonna go back to this. Probably this is the best slide. So as part of the Democratizing Models project, there are different languages where this effort will be done in. There will be an effort on Root trying to improve that side of it a little bit more for HSP. There's an effort that's happening on the Julia side. As far as I'm aware, nothing happens in Rust, even though I think Rust is probably one of the fastest things we have today, clearly because a lot of people are rewriting a lot of tools in Python and other languages into Rust because it's just performant and efficient. But a lot of it comes down to sort of this community buy-in. I think with Python right now, it's easier for me to get support or to have people contribute or have students contribute because most likely students will have done some sort of Python if they're using physics or they'll hit, Mathematica or MATLAB, they'll have some exposure to things like Matplotlib. So it's easier to get them started on something like this than to say, I'm going to write this all in Fortran. And, not many people are going to be familiar with being able to write in Fortran. I think even though Fortran likely would have been the fastest option, it doesn't do me as much good if I don't have other people helping me build up this project because it has to be a community effort. That's kind of the main driving thing. So you can say, yeah, Python may not be the fastest, but it makes up for it by having such a larger community involved, this huge scientific Python community, which is, I would say, quite mature at this point. But thus, that might be naive of me to say.
Thank you.
I have a additional question building off Doha's. You mentioned that you were using Rustwork X instead of Network X in Python. And I was curious, at any point, did you use Network X? And how much faster was it once you switched?
Yeah, so Network X, one of the reasons I didn't want to pick it was the installation was a little bit annoying. It had a lot of compile things, and I just found RustWork X much, much better for significantly larger computational graphs. And for whatever reason, I don't quite understand. Some of it comes down to something like the first class language support and Rust compared to C++ for these things, even though the the graph algorithm, the network algorithms that you implement are the same. Those are just in some random textbook that you pull off the shelf, you blow off the dot, and you just write it in that language. That's not going to change. It's something about the language that really improves the performance there. And that's the main reason I trust it. I mean, plus there's also the benefit that it's in Rust, so it's faster and much more portable.
Fantastic. Thank you. Hey, Tom?
So has there been any adoption of PyHS3 in fields outside of particle physics? Because a lot of these problems of fitting a spectrum look a lot like what some of our beamlines do in terms of either the fluorescence beamlines or the powder diffraction beamlines, where you're building up a histogram and then fitting it to a somewhat complicated model.
Yes, so there is adoption, and I'm showing this slide specifically because HS3, uh, do you see the slide?
Do not.
Oh, okay. No?
You may
Oh,
need to just re-share your screen. Perfect.
okay. Sorry. So this particular slide here, I don't know what happened, but this particular slide, we have the Democratizer Models Project, and the goal there is to increase the adoption of HS3. HS3 is relatively young, but adoption will be not just in particle physics, but in hadron physics, nuclear physics, astrophysics, astroparticle physics, and laser physics. We have key stakeholders within each of those particular domains who are contributing to this project, who are getting funded to develop the usage of HS3 within their particular domain and put together a central web portal that makes all of this accessible for everybody. I don't know if that particularly answers your question. I would say the answer is there's no wide adoption right now. It is foreseen that there will be adoption.
Yep.
And then, James, did you also have a question?
I have a somewhat provocative line of inquiry down the same path that I think Tom took. When I see a presentation like the one that we saw today, I naturally, as a non-physicist, am drawn to the aspects that are very similar across all software. So I see the NumPy aspects, I see some of the packaging aspects, and I say, ultimately, is all physics just the same amount of NumPy and pandas and matplotlib code? But in truth, we have among our panelists people representing three different light sources or three different accelerators, and presumably the nature of the work at LHC, APS, and SLS2 is quite distinct. My question is, how do we see that in the software itself? What kind of softwares exist only for the purposes of fundamental particle physics at LHC, and how are those very different than the ones that we see at APS or NSLS2? And as a non-physicist, how can I better appreciate the needs of a physicist in the types of software they have to create?
I am not as familiar with the software being used outside of, like what LCLS2 is using, and probably, Tom can answer some of that. But I would say there are specific packages I am reasonably confident that everybody is using no matter what. such as NumPy, Matplotlib, SciPy, I think would be the three common baseline packages that feed into everything else. But if you're asking about, could somebody else, like say LCLS, to come up with their own HS3 package, I'm sure they could. Nothing's really stopping them. I hope that we try to centralize a little bit, but physicists can't be stubborn, and I think as a community within the U.S., some of that might come up to the funding agency driving some of the decisions being made here, but theory and NSF could have some leeway in saying the money that we're providing you, you can't be developing brand new packages. You need to do your best to contribute or use existing packages, try to centralize the effort a little bit. But again, there's no motivation, and partly why I like Python. There's nothing that stops me from creating my own package and contributing to the ecosystem. I don't know if there should be, because I like the freedom that it buys me, but it comes at a cost, and the cost would be, you know, fractured support, perhaps. I don't know if that helps answer your question, or if there's something more specific you're looking.
I think any feedback that helps me better appreciate the uniqueness of the work that the different types of physicists do is very helpful, because in retrospect, I think that sometimes as a non-physicist, we sometimes have perhaps an arrogant perspective that the software is all the same, we just teach it all the same, use it all the same. What are you moaning about? But in truth, there must be very significant differences in the use cases that then bleeds over into the software itself.
I can say something. I think a lot of what makes an API nice to use is how closely the assumptions the API makes matches your own assumptions and your own needs. And there's some tools where if you assume that all of your data is always going to be a multi-page TIFF stack because you do time series of images, even if under the hood what you're doing is statistical fitting, if the only thing you take as input is a image stack, that's going to be not legible to someone whose data comes in looking like a table. Or conversely, when you get to these big data formats, the file formats or the APIs that are supported by the tools out of the box, if the first step to learning to use this new package is learning roots file structure, that may be a high barrier to adopting that tool outside of high energy physics. That got rambling, I apologize.
If I may chase that line of thought very slightly, it occurs to me then that the softwares are going to reflect the traditional modes of analysis, the traditional physical studies that are done. And so does that mean that the APIs that are created are often reflective of a pre-computational approach, not reinvented in terms of the computational approach? Like, do people write software like PyHS3 to mimic how they did the analysis before that kind of software existed? Or do they reinvent everything from scratch because now they can analyze much larger sets of data in very different ways?
You're muted.
By internet connections. At the level of root, all of these teams right now are using their own sort of statistical analysis package. There's so many names I can rattle off, but that's not really useful. Within Atlas, within CMS, we all have our own favorite way of, building up our statistical models, what we call model builders effectively. They come from where you load in some sort of root file or you define your selection and your list of systematic, and it does kind of all the bookkeeping and kind of goes, ta-da, here's your statistical model. thus at the level of what's called a root-style root workspace. HS3 implemented in root means that up to some point, even now, root could export this by just saving it to a root file. But it's a binary format, it changes, it's susceptible to being broken over time with major root version, has happened. And it's not, I can't open it up in my little favorite editor and look at it because it's binary. But the alternative is having HS3, which is a plain text serialization of that same workspace. That was always able to be serialized in root, but can also export to some plain text like YAML or JSON or BSON or what have you. That's the slight change. And it's sort of changing those small pieces of things people already depend on. Because I think Tom kind of already mentioned it, it's really hard to get people to learn a new tool or a new package because things are just a little bit different, a little bit opinionated. But swapping out pieces that those packages depend on without changing that entire workflow and getting people step by step edging over, I think it's always going to be a better way of moving forward. And that's kind of where I see, a tool like PyHS3. That's why I said it's not going to do minimization or anything for you. It's giving you a function you can call the likelihood on to calculate it. Because then I say, okay, this exists now in Python. Build on top of it. That API should not change much. And this tool will figure out or deal with the evolving of the HS3 spec for you. It'll deal with whatever Root's doing to change how Root serializes things because Root injects some of its own opinions into HS3. PyHS3 will be aware of that, so you don't need to be. You can then say, build your own model builder in Python on top of all this if you wanted to. If you wanted to shun the 30 or 40 that we have in Atlas already and make your own, you can certainly do so, and then export that onto HS3 back into Root and use the existing Root minimizers that you have. It's trying to make this all as flexible as possible to give people options because if you don't have options, it puts more burden on the people who maintain the software to meet all the people and all the individual needs across all the different computing facilities that we provide. And on some level, it's hard.
That was an amazing answer about just being open and transparent as possible with your models, and then also meeting your users where they are at and not telling them that the technical barrier to do the things that they want to do is all the way up here. Instead, we can bump it down just a little bit, and that means even more people get to participate. I want to thank our guest panelist, Dr. Giordon Stark, who has done an amazing job sharing all about the tools, PyHS3, that are enabling science to be more transparent and more accessible. I also want to thank our host panelists, Doha, Tom, and James. It is a pleasure having you join us time after time. And if you're in our audience and you want to find out about upcoming Python exchanges, please check out our website. That is meetup.doepy.org. Next month, we're going to be joined by Philip Rudiger from the HoloViz team. So if you do a little bit of data visualization, you may be familiar with his work. I want to thank you all for joining us and look forward to seeing you again next month. Thank you, everyone, and have a fantastic rest of your day.